Okay, we're going to review graphing techniques. This is something that you've done all along through school, but we really use graph and graph interpretation lots in Physics 20 and in Physics 30. So we're going to make sure that you understand it before we get too far into it. So you need to select your axes, and we typically work on an X and Y axis. On the X axis is the manipulating variable. It's the component that you control. If you're trying to see how far something goes in a specific period of time, you're controlling at what time intervals you're going to measure that distance at. So the time would go on the X axis. And the responding variable, which is the one which is changing, so for in our example the distance, then that would go on the Y axis. And you always label the axis with a name and the units. It does me no good to tell me that this is time. Is it in seconds? Is it in minutes? Is it in hours? It changes the graph that we're looking at. Always select a scale so that you end up with 2/3 minimum of using your graph in both the X and the Y direction. It doesn't mean that you would fold it up and it would then be 2/3. Use 2/3 of your paper. And for most of the graphing paper that we use, I believe it's 20 squares going across if you were to have your paper hot dog style, and it would be, I believe, 35 or 40 going up and down if you had it looking like the paper that you're holding right now. Okay, and always use a scale that's consistent. If each division is 1, then it's 1 across the whole point. So 1, 2, 3, 4, 5. You can't go 1, 2, 3, jump a few, 10, 11, 12, 13. It can't go that way. Each line division that you pick an interval at has to increase by exactly the same increments. You plot your points according to your X and Y coordinates that you're using, and then you draw a line of best fit. And the line of best fit doesn't necessarily force everything through 0. It's the one that represents the trend of all of the plotted points. So it represents an average. And you can have a straight point and we can ignore it, but usually the trend acceptance for a line is 19 out of 20 data points has to be accounted for. You can have one that's just out there and you don't really have to explain why it's out there, but the other 19 points you do. And so this is a statistical thing that you'll learn later on as you go through your post-secondary education. And we call those sources of errors. So can we explain why that point was out? There's two terms that we're going to use, interpolation and extrapolation. So interpolation is the data that we see in between the points. So on the graph between your lowest plotted point and your highest plotted point, the data in between there, when it doesn't cross an actual data point, we interpolate that data. If we need to go beyond the lowest point or the highest point and we need to kind of guess how that line keeps going in that same straight line, that's called extrapolation. You need to have a title of your graph, and it's always Y versus X. So time versus distance, or whatever you want it to be. We have to be able to understand what those data points are on the graph. If we just see a graph that has points on it, we could interpret it to mean whatever we want unless you're specific in labeling your X and Y axis as well as labeling your whole entire graph. We're going to determine the slope, and if you remember the slope formula, the slope line formula is Y equals mx plus b. And to figure out slope, it's rise over run, which means that we're going to look at our Y coordinates over our X coordinates, and it's going to be the change in. So y2 minus y1 all over x2 minus x1. This becomes really critical the further we go into physics when we look at kinematics and dynamics. Okay? Another way that we can see this is m times y2 minus y1 is equal to x2 minus x1. Okay? No, have those backwards. Ah. Okay? x2 minus x1 is equal to y2 minus y1. Okay? Point A is going to be x2, y2, and point B, I have that backwards, x1, y1, and point B is x2, y2. Okay, that's pretty much a review, but if not, now you have it. Okay, this is really critical right here. A lot of people make this mistake. Use points that are on the best fit line. Okay, and not your actual data points, because you might pick data points that when we draw our best fit line don't even come close to that line, and then your information is skewed. Okay, always include your units, because from your units we can figure out what you're looking at, and we can also double check that we're figuring out the right thing. Use 2 points that are far away from each other to get better representation. So on a graph like this, you want your point here and your point here. Always inside of your, if those are your, green is your original data points, always use data from inside your data points. Okay? Show your work, and the physics equation will be able to fit into the straight line. Okay? So then this would be this is going to be your y variable. This we know is your slope. This is your x variable. And this is going to be your y-intercept. Now I know that you'll do a lot of this work with Mrs. Goodall, but I don't know that you're there yet. Okay? So, arrhythmia, which we know to be an irregular heartbeat, data is measured and the number of heartbeats over an elapsed period of time of a patient who has arrhythmia. For the most part, this is the standard way of doing it. You put your x components here and your y component here. What's being manipulated? What's responding? Every 10 seconds, we're going to take a heartbeat reading. Manipulated, responding. X, y. Plot an appropriate graph of the data. I believe I included graph paper in your note packet. And so what you'll see here is that using 2/3 of the scale, we have this graph. And so here is our x variable. You can see that every 5 lines they've done, or every 10 points, they've done 10, every 5. They've done 10, 20, 30, 40, 50, 60. Time is in seconds. What's responding is the number of heartbeats, and they've gone every 5, 10, 20, 30, 40, 50, and they've plotted it. And you can see, that they've taken a data point here and a data point here. This data point, if you wanted to be more accurate, should have come from up here, inside your data points. This is extrapolated here. Our first data point is here, so anything between these points here is interpolated. Anything here, anything here and anything in the top corner is extrapolated. And so this data point should have actually come from in here. Okay, we know that this is number of heartbeats, and this is the title of the graph. Number of heartbeats versus time. Nothing elaborate. We're taking the definition of our y graph, the definition of our y-axis, and the definition of our x-axis, and we created a title. Okay? Determine the slope of the line. What does the slope represent? So slope equals y2 minus y1 over x2 minus x1. And you can pull whatever data points you want, but make sure they're inside. The example in your note packet is not the best example, like I said. But they picked data points A as being 6 and 6, and data point B as being 36 and 38. And typically, you want to choose points that are on an actual intersection on your graph, not one where you have to extrapolate data, which could be why they picked that 6 and 6. But that's extrapolated. That's not interpolated. Okay, so we have 38 minus 6 over 6, oops, 36 minus 6, which gives us 32 over 6. Which is equal to the slope, m is equal to 0.06, repeating, beats, remember this is the number of beats, and this is seconds, so this is beats per second. That's our unit. We don't even have to have a formula. We can figure out the units from the graph. Okay? And so, what do we know beats per second to be? We know beats per second gives us a heart rate. I'm sure you've all done this in phys ed where you've taken your heart rate and you've taken it over 10 seconds, you multiply it by 6. Slope is equal to heart rate. Okay? So when you take your heart rate, you're doing physics and you don't even know it. What is the average heart rate at 45 seconds? Well, we can use our slope. Okay? Because our heart rate, we say right here that our heart rate is our slope. And our slope is constant. It's a linear line. So therefore, it's 1.06 heartbeats per second. Or 107, if you want to round it up. Okay? If our line went like this, we'd have to do something different. But it doesn't. We have a linear line, which means that it's never changing. Which means that it's 1.07 heartbeats at 1 second and it's 1.07 heartbeats at 45 seconds. And so the linear equation for the graph, y equals mx plus b. Our y variable is equal to 1.07. I'm going to round it up now. X. And we see that on the graph the line goes through 0. So 0 can be written as, okay, either one is correct. This is a true line formula, and this is modified. What would be the average number of heartbeats in a time period of 175 seconds? Is this interpolation or extrapolation? So that y equals the number of heartbeats, x equals time. And our formula is y equals 1.07 x. So y is equal to 1.07 times 175.0. Right? So this is heartbeats per second times seconds. When we look at unit analysis, seconds divided by seconds is 1. We're left with heartbeats. Y is equal to 87 heartbeats. Okay? So I'm not going to give you the page 15 for homework, but I am going to give you the graphing homework. And you can work on this and the rearranging equations for the rest of the class, and it'll be due at the beginning of the next class.